Right. Good morning, everybody. Let's go ahead and start. So first off, are there any questions on material that we've covered up to this point? Or questions on things that you might be encountering in your homework problems? All right. If questions come up later, maybe there will be another opportunity at the end of class where we can go through some things. What I wanted to do today was take a shot at understanding the nature of some of those cyclic point groups, because if you were looking through your character tables, they may have looked rather different because the characters in those cyclic point groups were not simply integers. You could see that there were exponentials. And so, that would look pretty bewildering at first, right? So we want to try and tackle that and try to have a little bit more understanding of those cyclic groups. So let's do that. So if we're making the character table, and we can take the point group C5 as an example, we note that, of course, the C5 operations are C1-5, C2-5, C3-5, C4-5, and C5-5. And then our job would be to construct irreducible representations for this group. Now, seeing that this is a cyclic group, all of the elements are in their own symmetry class. So given the 5 symmetry classes, we need 5 representations for the irreducible representations. So we've got 1, 2, 3, 4, and 5. Okay. And furthermore, we know that the dimensionality for these irreducible representations, when we take the sum of the squares of the dimensions of the irreducible representations, they must equal to the order of the group, which in this case is 5, right? So we should have a value of 1 for the E symmetry class, right? And of course, C5-5 is E. We know that. And so we would expect the characters here to be 1. All right. But what about the other characters? Okay. So when we do a rotation, we understand if we align the C5 along the z-axis, X and Y transform according to the matrix that might look something like this. We're going counterclockwise. Right, so this just transforms X and Y. Z stays the same. Right? And so you might expect that the characters here would be derived by taking the sum of the diagonals terms, so 2 times the cosine of theta. But if we do that, we're going to have some non-integer values, and we would find, as we've seen before, with symmetry operations, where n is an odd number, we need to have something higher than a one-dimensional representation to construct the irreducible representation. We saw that, for example, in the C3V point group. We need a two-dimensional representation in that character table. But if we have two-dimensional irreducible representations in the point group C5, and I know that I have to have 5 irreducible representations, I run into a problem. Okay? So we need something else. We need another tool to satisfy the dimensionality of the irreducible representations, yet be able to produce characters for the irreducible representations in this group. Okay. So what we'll do, if for the C5, theta equals 2 pi over 5, right? 1/5 of the circle. And then if we note the way this is transforming, if I just take as an illustration some kind of a unit circle here. If I have a value x and I rotate by 2 pi over 5, I of course get a projection back on x, which is equal to, say this is 2 pi over 5. The projection back on x is the cosine. So I have x cosine theta. So that part remains x in nature, but then I have an orthogonal component, which we have been designating as y, but we can call this an imaginary component, and that will be the sine of theta. Okay? So x, we don't even need the x here. So as I rotate by counterclockwise 2 pi over 5, I have my component x cosine theta, and then an imaginary component y, the sine of theta. All right? And so it turns out that if I have this expression, I can rewrite this based on, I guess, Euler's identity. And I don't know if you've seen this. Some of you may not have seen this. But this would be equal to E times 2 pi over 5 times I for theta equals 2 pi over 5. Okay. So I have an exponential e to the 2 pi over 5I equals this. Okay. So I did not know that identity for a very long time until I started encountering these problems. So if you haven't seen it before, don't be surprised. If you've seen it before, you might already have an appreciation for the I guess, the concept here and what makes it interesting. Its relation to the n roots of unity and the unit circle and trigonometric functions. There's a very sort of interesting mathematics related to this. But if we accept this, then we can use substitutions when we write the characters for our point group. All right. So what we can do is say for the symmetry class C15, we'll have an irreducible representation, and I'm just going to abbreviate this with the letter epsilon. That's what they use in the book, so I'll just pick an epsilon to equal this value. And if I say I have epsilon once, that will be the character for C15 for the first irreducible representation. And then if I take it twice and 3 times, so that I have the following characters under the class C15, then I can begin to write the remaining characters of the irreducible representations by simply taking the square, cube, 4th power, and 5th power of the character under the first C1 operation. Okay. So this is simply a rotation by theta to give you a real component along the original value x, and then an imaginary component orthogonal to x. We typically call this y, but we can express that as an imaginary or orthogonal component, which creates the form of a complex number. Okay? That complex number will be, we'll use that specific feature of this value in solving this cyclic point group. All right. So the next step here, if we accept this, is to just take the squares, cubes, fourth power, and fifth power of the first character in the representation. So this will go epsilon squared, epsilon cubed, epsilon to the fourth, epsilon to the fifth. And then if I square the epsilon squared here, I get epsilon to the fourth. If I take the cube, I have epsilon to the sixth, epsilon to the eighth, and then epsilon to the 10th. So remember, if I'm multiplying exponents, I just add, what am I saying? Squared and squared, I just add, or multiply the exponents. All right, so if I have the cube and square it, I get epsilon to the sixth. If I cube that, I have epsilon to the ninth. If I take the fourth power of epsilon cubed, I have epsilon to the 12th, epsilon to the 15th here. And then you can see I just fill out the table accordingly. So the square of epsilon to the fourth is epsilon to the 8th. The cube will be epsilon to the 12th. The fourth power of epsilon to the fourth will be epsilon to the 16th. And then the fifth power of epsilon to the fourth will be epsilon to the 20th. And then these values will be epsilon to the 10th, epsilon to the 15th, epsilon to the 20th, and epsilon to the 25th. Okay? So that part is relatively straightforward, and you can get to a table that looks like this. Okay? So some of the other 5 rules, among the other 5 rules governing the properties of irreducible representations, we need to show that any 2 of these are orthonormal. So that is, if I take the character of one representation as a product with the character of another representation under the symmetry class times the order of the class, which is always 1 here, and then I add up those products, I should have a final value of 0. So, for example, is the representation 1 orthogonal to the representation 2? Okay, so we should test that and make sure this holds up, otherwise we have a problem. And so that would mean epsilon 1, epsilon 2, plus epsilon 2, epsilon 4, plus epsilon 3, epsilon 6, plus epsilon 4, epsilon 8, plus epsilon 5, epsilon 10 equals 0. Okay? So I'm just taking the products here. And so that goes to epsilon cubed, epsilon 6, epsilon 9, epsilon 12, epsilon 15 equals 0. All right. And let's take this and simplify it a little bit. So notice if we have epsilon is equal to e times the 2 pi I over 5. If I take this to some power that is a multiple of 5, then I multiply the exponent by 5n, right? And then when I do that, I end up with some multiple of e to the 2 pi I, because the 5 cancels out. in the numerator and denominator of the exponent. So I have e 2 pi I over times n. It doesn't matter what integer value n is equal to. As long as this is a multiple of 5, then I have the special relationship of the Euler's identity. So note the Euler identity, which is a really interesting feature of mathematics, I guess. E to the 2 pi I is equal to 1. That's one way to express the identity. All right. So if we take this mathematical theorem and apply it to our expression here, we see that for if epsilon to the 5th power is equal to 1, and any multiple of epsilon to the 5th power is equal to 1, we can reduce these exponents to simpler form. So this then becomes epsilon cubed. This is equal to epsilon to the 5th times epsilon. Epsilon to the 5th is 1, so this goes to epsilon. Right? And then this is epsilon to the 4th times epsilon to the 5th. Epsilon to the 5th is 1, so this reduces to epsilon to the 4th. This reduces to epsilon to the 2nd power, and then this goes to 1. And if you wanted to rearrange that, you can see that this is epsilon, epsilon squared, epsilon cubed, epsilon to the 4th plus 1 equals 0, right? So that's because of the Euler's identity. So is this true? And if we go back to our circle here and we draw, this is 2 pi over 5. If we go opposite in direction in this rotation, this is 8 pi over 5, right? And then if I go this way and then this way, this is 4 pi over 5, this is 6 pi over 5 in our circle. So then if I substitute my values here, I get a sum of, so if epsilon is cosine 2 pi over 5 plus I sine 2 pi over 5 plus cosine 4 pi over 5 plus I sine 4 pi over 5 plus cosine 6 pi over 5 plus I sine 6 pi over 5 plus cosine 8 pi over 5 plus I sine 8 pi over 5 plus 1 equals 0. So we're still trying to prove that these are orthogonal. So I just substituted back here. And I can basically group these together just sort of out of convenience. So cosine of 2 pi over 5 plus cosine 4 pi over 5 plus cosine 6 pi over 5 plus cosine 8 pi over 5 plus I times the sine terms, 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5. Okay. Let's go to this unit circle here and try to understand these terms just visually, right? So I always have opposites in terms of the angular rotation. I could take a clockwise 2 pi over 5 or a counterclockwise 2 pi over 5, and that will be the 8 pi over 5, right? So notice the sine terms are always equal and opposite in value, right? Here's the sine of 4 pi over 5. Here's the sine of 6 pi over 5. So those pairs cancel out, and this term basically goes to 0, right? And you didn't even have to compute it. You could just look at it visually here as one way of solving that. But if you type that into a calculator and put in these specific angles, you'll see that it'll go to 0. So the imaginary component drops off to 0. The remaining component, whoops, and I forgot the final term here. Excuse me. This series of cosines plus 1 must be equal to 0. And so in our unit circle here, we're going to say that the value 1 plus the cosine of 2 pi over 5, which is the same as cosine of 8 pi over 5. It's this distance here, so we're going to take 2 of those short distances. We're saying that that's equal to the cosine of 4 pi over 5, which is this distance here, which is the same as cosine 6 pi over 5. So 2 of those should equal to 0. Okay? And you can calculate that and verify that that's true, but when you add up these 5 terms, it equals to 0. And so you can really show that these are orthogonal, and you can do that for any set of 2 irreducible representations as they're written in this form. That will work out. Okay? So basically I just did that to convince you that we're following the rules of the great orthogonality theorem, or the 5 rules pertaining to irreducible representations and groups. That's what this is about. So now if we're happy with that, we can go now to this table and take advantage of the Euler's identity, and we can simplify the entries here, right? So anything over e to the 5th will simplify because multiples of e to the 5th go to 1. So this term here goes to 1. And in this column, which basically pertains to the identity element, right, and the identity operation, since all of these epsilons have the exponents multiples of 5, these terms all go to 1. And now we indeed have 5 irreducible representations, and the sum of the squares of the dimensions of those representations is equal to the order of the group. So we're satisfying the rules of irreducible representations. So then we can go through and simplify these expressions. Epsilon of the 6th just drops to epsilon. Epsilon of the 8th goes to epsilon cubed. Does that make sense? I didn't trick anybody? All right. Epsilon of the 6th goes to epsilon. Epsilon of the 9th goes to epsilon to the 4th. Epsilon of the 12th power goes to epsilon squared. And now you might start to see that there's a pattern. All the terms are just epsilon. It's basically this set of values, right? Epsilon of the 8th goes to epsilon cubed. This goes to epsilon squared, and this goes to epsilon. Okay? And these are all, the exponents are all multiples of 5. So all of those terms go to 1. And that provides the fully symmetric representation. We always see this representation in any point group where all the characters are 1. Okay? So now it's starting to look more and more like an actual character table for the other point groups we've been working with. Okay? I need to make some space. So we showed it's orthogonal. I can get rid of this. All right, so we've been able to rewrite the table. And now to further, to complete this, it can be shown that there are pairs of epsilons that are in fact complex conjugates, and we will group them together. So there are pairs of epsilon and n that are complex conjugates. And so, for example, epsilon and epsilon to the fourth are complex conjugates. Epsilon squared and epsilon cubed are complex conjugates. So what does that mean? Okay, so epsilon, first of all, a complex conjugate is if I have a plus ib. This is a complex number. If I multiply it by its complex conjugate, that will be the form a minus ib. Then you get the difference of two squares. Now I said difference of two squares, but I have a positive here. Do you know why that is? Do you remember what I is? Have you seen that before? So if I have the term minus I squared b squared, the I squared term goes to minus 1, which cancels the minus. Okay, good. So you can show that these pairs are in fact complex conjugates of one another. Isn't that kind of strange that it works out like this? So you can look at this a little bit more. So if epsilon to the fourth is equal to cosine 8 pi over 5 plus I sine 8 pi over 5, right? And then epsilon equals cosine 2 pi over 5 plus I sine 2 pi over 5. If we claim that these are complex conjugates, then we can say something like how did I put it? Just checking my notes. The complex conjugate of epsilon to the fourth equals epsilon to the fourth star. So we use a star as a notation for complex conjugate. Epsilon 4 star equals cosine 8 pi over 5 minus I sine 8 pi over 5. And we're going to claim that this is equal to epsilon. We're going to show that these are complex conjugates. So that has to equal cosine 2 pi over 5 plus I sine 2 pi over 5. Okay, so then in this equality here, if we go back to the unit circle, we see that the cosine of 2 pi over 5 and the cosine of 8 pi over 5 are exactly the same, right? This is equal to this. So those terms will cancel. So if I just write, as a reminder, cosine 8 pi over 5 equals cosine 2 pi over 5. These cancel. So then we have minus I sine 8 pi over 5 equals I sine 2 pi over 5. Right? And then if I add these together, so I add this term to both sides, zero is equal to I times sine 2 pi over 5 plus 8 pi over 5, which is basically equal to I sine of 2 pi. Because when you add 2 pi and 8 pi over 5, you get 2 pi, a full circle. And then the sine of not rotating or rotating any integer value of a full circle is 0. So sine 2 pi goes to 0. We have now shown that epsilon and epsilon to the fourth are complex conjugates. So it's a special relation. And then we can just simplify the notation and say that instead of the complex conjugate of epsilon being epsilon to the fourth, we'll just say epsilon star equals epsilon to the fourth. Right? And then we have the terms epsilon 2 star, the complex conjugate of epsilon squared, is equal to epsilon cubed. So we have pairs now of complex conjugates, and I can rewrite this whole table where I regroup everything. I will have on its own the fully symmetric irreducible representation, an A1 type irreducible representation. Okay. Let's go erase this, I guess. Let's just rewrite this point group to a little bit more familiar way, where we put the identity operation first, followed by the other operations. So C5, we have identity, C15, C25, C35, C45, and we'll take the fifth irreducible representation that we constructed with, and just bring that up here as the A1 irreducible representation. Right? And now we're going to take pairs of the other two, or the pairs of the other four remaining irreducible representations, where within the pair we have, under each symmetry class, complex conjugates grouped together. So for example, if I take the first and the fourth representations, and I group them together, I'll have, for the representation 1, and maybe I'll just write it out like this. So I have epsilon squared. We see that epsilon cubed is a complex conjugate of epsilon squared, so we write E2 star. And then we know that epsilon to the fourth is a complex conjugate of epsilon, so we'll write E star. And then 1. Oops. I need to shift all these over because I moved E over here. I have 1 epsilon under C5 epsilon squared under C25. I have epsilon cubed under C35, which is the complex conjugate of epsilon squared. And then I have epsilon to the fourth under C45, which is the complex conjugate of epsilon. So my terms look like this. And then I'm going to pair this with the fourth irreducible representation. Remember, I brought E to the left side, so the character there is 1. Under C15, I have epsilon to the fourth, which is the complex conjugate of epsilon, so I write E star. And so I've grouped, under the symmetry class, the complex conjugates for the character of the irreducible representation. So without even looking, I would guess that this should be the complex conjugate of epsilon squared, which is epsilon cubed. And if I go back to the fourth irreducible representation under the class C25, I have epsilon cubed. Right? So then this should be epsilon squared, and this should be epsilon. Boom, boom. Okay? So this pair, I will group them together and call it the E1 irreducible representation, which was formerly the first and the fourth irreducible representations in this table. All right? So this allows me to maintain some of the rules of irreducible representations. I know that I have to have 5, right? Because I have 5 symmetry classes. I know that the sum of the squares of the dimensions must equal to the order of the class, or the order of the group, 5. So I need to have 5 representations, and the value under the symmetry class E must be 1, right? So it allows me to do that. These are grouped together given the symbol E1, and I'll show you in a moment that if I take the two components here of the E representation and just add them together, I would have the normal characters that I would expect under each symmetry class. They would be non-integer values, of course, but they would be matching with the transformation matrix that I would expect for these rotations. So I can show that in just a moment. Let's finish the other two irreducible representations. So we have 2 and 3 here. So if I just take representation 2, representation 3, under C15, I have epsilon squared. Under C25, I have epsilon the fourth, the complex conjugate of E. Oops, this should be squared here, right? Then I have epsilon, and then I have the complex conjugate of epsilon squared. All right? And then for the third irreducible representation, I have complex conjugate of epsilon squared. Then I have epsilon. That makes sense because I have epsilon star here. And then I have epsilon the fourth, which is E star. And then under C45, I have epsilon squared. So you can see that within these two entries, I have complex conjugates grouped together, and then that will be the basis for an E2 set with the original representations 2 and 3 composing that. All right? And so this one's E1 simply because you have epsilon the first power here. This one's E2 simply because you have epsilon the second power here. That's it. It's a small formality. All right. So this form of the character table satisfies the 5 rules of irreducible representations. And then if you simply add up the terms, so if I just take the E1 set of terms and generate characters as a result of adding these, we see that I have a 2-dimensional representation under C15, epsilon plus epsilon star. Remember, that's going to be cosine 2 pi over 5 plus I sine 2 pi over 5 plus the complex conjugate, which is cosine 2 pi over 5 minus I sine 2 pi over 5. So those two cancel, right? And you just simply have 2 cosine theta, where theta is the angle of rotation. And that's exactly what we expect from the transformation matrix. Remember, when we write the transformation matrix for x, y, z, you have cosine theta minus sine theta, 0, sine theta, cosine theta, 0, 0, 0, 1. Now I'm making an irreducible representation of dimensionality 2, and this block diagonalizes, so that's a 1 by 1 corresponding to the z as a basis, but x and y are the basis for this 2-dimensional matrix. And the character of that matrix, this 2 by 2, equals 2 cosine theta. That's exactly what we have here, right? So when we combine these terms, you have the correct character for the transformation matrix for doing all of these rotations. It's only when you combine those complex conjugates. Okay? So, in short, there's a lot of mathematical wizardry, I think, in all of this. It's very fascinating. It's very strange. I think the whole idea here of the unit circle, the n roots of unity, the Euler's identity sort of gives you a hint of a very deep, expansive mathematics. That's kind of beyond, the subject of this course, but those tools allow us to see how the cyclic character tables, the character tables for like Cn point groups are derived. And I wanted you to see that mainly because I think it's fascinating. There is a practical sense. I will not ask you to derive something like this on an exam. I think it's too much for the in-class exam. But I would invite you to just try it out and be less afraid of looking at those character tables for, say, the Cn point groups or other point groups where you might see these complex conjugates grouped together into different terms that are greater than 1 dimension. All right. So that's it. I'm going to stop the recording.